Today's video lecture is the second part of our lecture on the inverse Z transform. And the main goal here is to see how we can find the inverse Z transform for non-rational functions. And to do that, we will first talk about the Z transform of power series, and then I will talk about application on how to find the inverse Z transform of non-rational function by using their Taylor series expansion. Let's start with a power series. So maybe we start with an example. So here you can see the question is find the inverse Z transform of this function. X of Z is equal to 4Z cubed plus 2Z squared plus 1/4 Z plus 1 plus 2Z minus 1 plus Z minus 2. And I hope that you can see easily what the signal is. So the signal here is the following. So I'm gonna draw it here. So at 0 is 1, and at -1 or at +1 is the value is 2, and at n equal to 2 the value is 1 because it's 1 here, and then you can work your way backward also. So here is 1/4, so at -1 the value is 1/4, and -2 is 2, and -3 is 4. And this is exactly what the inverse is. So this is the signal. So the inverse of a power series is easy because the coefficient of each power gives us the value of the signal. And now we can write the signal in a delta function notation. So I have x of n to be equal to 4 delta n minus 3. Here n plus 3 plus 2 delta n plus 2 plus 1/4 delta n plus 1 plus 1 plus 1 delta n plus 2 delta n minus 1 plus 1 delta n minus 2. And this is the signal. So this is basically the inverse of a power series. And here you can see the answer maybe in a cleaner way also. So power series, you just read the coefficient here. The negative of it gives you the time. So this is n equal to 2. And the coefficient here, which is 1, gives you the value of the signal. And although this looks immediate, but this is going to be very helpful when finding the inverse Z transform of more complicated functions. So let us start talking about how to find the inverse function of a general function. Here, for instance, in this example, we have x of z equal to log 1 plus a z minus 1 with the norm of z larger than a. You can immediately see that this is an autorational function, so I cannot apply what I learned in part 1 of this lecture. And the question is, how can I find the inverse Z transform of this function? Now, the trick is actually to transform this complicated function, or maybe non-rational function, into a function, into a power series, and then to do exactly what we did in the previous example. And to find the power series expansion, we need to use the Taylor series expansion. So let me remind you here, what do I mean by Taylor series? So maybe I'm gonna give a little bit formal definition, but then I'll try to explain it a little bit in more detail. So the Taylor series of a real or complex valued function f of x at a real or complex number a, so the Taylor series at a point a, this is important, is the following power series. So you can think of it as an approximation of the function a. So this is the Taylor series, and using this summation approximation. And basically what the result that we have is that, or what makes it interesting is that the function f of x or the function f of x is roughly, or can be approximated by its Taylor expansion, f of a plus f prime of a divided by 1 factorial x minus a, and so on and so forth, when x is very close to a. So that's basically why Taylor series is interesting. So for example, one famous Taylor series that you should know is the Taylor series expansion of e of x, and this is the Taylor series expansion at 0. So maybe let me ask it like a question here. So find the Taylor series expansion of e of x at x equal to 0. So of course, if you want to approximate e of x, so let me just apply the formula here. So I know that the Taylor series expansion of e of x 0 is first e of 0, so f of 0 here, right? So I'm applying here. This is f of a, so f of 0 is 1. And then I need f prime of a, so f prime of x is also e of x, and then f prime of 0 is also 1. And actually, if you look at all the derivatives are going to be the same. So f at any order, any nth order derivative of x is equal to e of x, and therefore the nth order derivative at 0 is always equal to 1. So if you apply the formula, you will get the following. So e of x is equal to sum from n equal to 0. Well, actually, it's not e of x equals. So the Taylor expansion is the sum from n equal to 0 to infinity. Fn of a is 1, so and a is 0, so it's going to be xn divided by n factorial. So that's basically the Taylor series expansion of e of x. Now, the Taylor's theorem says that when x is closer to 0, so if x, let me write here, if x is very close to 0, then e of x is roughly, or is a good approximation of e of x is this. So this is going to be 1 plus x2 divided by 2 factorial, and so on and so forth. So you can stop. The further you take this expansion, the closer you are to the real values. Now, similar to the Z transform, for Taylor series, we have a region of convergence. So it turns out here that e of x, not only when x close to 0, but you can show that e of x, it's a good approximation of e of x for any x. So the Taylor series of e of x at x equal to 0 is a good approximation of e of x for any x, and this is why we can write e of x is equal to sum from n equal to 0 to infinity, xn divided by n factorial for any x. Doesn't have to be x does not have to be close to 0. So I don't want to go into details why this is true, but you can find more information on, for example, Wikipedia. So in that sense, you can think of a Taylor series as an approximation of any function by a power series within a certain region of a convergence. So here for e of x, we're kind of lucky because the region of convergence is the whole z-plane. But in general, you may not have the whole space to be your region of convergence. So you're just restricted to being very close to the number where you're doing the Taylor series development. So now to give you a little bit, so we just did it here in a mechanical way, we just applied the formula, but if you want to know what's really happening, so think of it as you're trying to approximate your function. So let me use a different color here, so maybe I'll use the green color. So let's take the function e of x. So the function e of x looks something like this. So you have for x equal to 0, you go through 1, right? And then when x goes to minus infinity, you go to 0. And when x go to infinity, you go to 1. So maybe it's something like this. So or it is something like this, right? So that's e of x. Now what you're trying to do is actually trying to approximate e of x at x equal to 0. This is what you're doing when you say I'm finding the Taylor expansion. So what you want to do, you want to approximate e of x here at x equal to 0. So you know that at x equal to 0, f of x is equal to 1. Now the question is, what if x is close to 0? What is f of x? So maybe x is not 0, but maybe x is equal to 0.0 or 0.0001. So what is the best approximation? The best approximation, you could say, at least first order approximation, to say, well, if x is very small, then it's 0, then f of x is still 1, right? But you say, well, actually, it's not 1. It's 1 plus some correction term, because x is not 0. Now, to get the correction term, what you do is that you approximate your function by the tangent. You say, well, around 0, in this interval here, I'm going to approximate f of x by the tangent. So instead of f of x being the constant, f of x is now around the tangent, so f of x is going to be equal to here 1 plus x. So this is basically what you're doing here. So let me maybe highlight it in a different color. So if you look at the Taylor series here, your first order approximation is the constant, is the value of the function at a. So now the second order approximation is the tangent. You're saying, well, the function, if instead of taking the curvature of that function, you're just approximating it by the first order, by the tangent. Now you say, if you want more accuracy, what you're gonna do is that you find the error, you approximate the error. So for the second order, what you do is that you compute e of x minus, so far we have a 1 plus x, right? So that's a function. And then you do the same thing. You approximate this function again, and then again. So you keep approximating the error, and this is how you get this formula. So when you do this, when you subtract this term here, so you subtract these terms from e of x, and you approximate again by taking the derivative, then you get this term, and so on and so forth. So, sorry. This is basically the geometric interpretation of the Taylor series. Now let us find the Taylor series expansion of the function log 1 plus x at x equal to 0. So to find the Taylor expansion, we need to find the derivative of this function. So let me find the derivative. So I'll do it here in blue. So first I need to find f of 0, because I'm trying to find the expansion at 0. So I'm trying to find the Taylor series expansion of this function here. So f of 0 is log 1 plus 0, which is log of 1, which is 0. If I find f prime of x, then I'm gonna get 1 divided by 1 plus x, which is gonna be, so f prime of 0 is 1. If I find the second order derivative of x, this is gonna be, so this is, I think of this as minus 1 divided by 1 plus x squared. Let me double check that this is correct. Yes, this is correct. So then the second order derivative at 0 is equal to minus 1. And if I do it again, so the third order derivative is going to be equal to plus, so this is plus 2 divided by 1 plus x cubed. And so this is f of x. And then f cube of x is equal, at 0, is equal to 2. So I hope you can see the kind of, let me double check if I made a mistake here. No. So I hope you can see here that what we have is a pattern that we need to kind of see. So maybe if I do one more derivative, so if you do f of 4 what you're gonna get here, f4 of x, the fourth order derivative, you're gonna get, so 2 is a constant, so gonna be 2 is here, and you're gonna get a negative sign, and then you're gonna have times 3 times 1 over 1 plus x, 4, and hopefully, so f of 4 is 0 is, so I hope you can see that this is 3 factorial minus 3 factorial, minus 3 factorial. So actually, to see the pattern, this is actually 2 factorial, and this is minus 1 factorial, and so on and so forth. So I hope we can see here that f the nth order derivative is 0 at 0 is equal to, so for 4 I have a negative sign. So if the exponent here, or the order of degree is odd, then, or is even, then I have a negative sign. So this is gonna be minus 1 to the power n plus 1. Just to make sure that the sign is correct. So if n is even, I need to have a negative sign. And then since it is 4, then for the fourth order, the value is 3 factorial. So this should be, for the nth order, the value is n minus 1 factorial. Now, in general, if you want to do this rigorously, you need to prove it using the induction rule. But at least here you can see the pattern. And what does that mean? So now if I apply the formula, so I'm going to write it down at the bottom here. So if I apply the formula, so because I'm doing the expansion at x equal to 0, I know that the Taylor expansion is the following. So the Taylor expansion of this function is, I know that it's f of 0 plus the first order derivative divided by 1 factorial x plus the second order derivative divided by 2 factorial x squared, and so on and so forth. Or maybe it's easier to write it in using the summation. So this is the sum from n equal to 0 to infinity, f of fn of f0 divided by n factorial x to the power n. And now if I plug in the nth order derivative at 0, this will give me, this is the sum from n equal to 0 to infinity, minus 1 to the n plus 1 divided by n factorial, and then n minus 1 factorial xn. And now you can simplify by these two terms, and you get the formula here, which is sum from n equal to 0 to infinity minus 1 to the power n plus 1 divided by n xn. Now if you compare it to what I have here, you can see it's the same formula here, but it starts at n equal to 1. So let me double check. Yeah, there's a little bit here, I cannot divide by 0, so I may have made a mistake. So this formula here is true for starting n equal to 1. So yeah, because f of 0 is 0, right? So f of 0 is 0, so it doesn't count here. So I had to start, I made a typo here. So here, so this is f of 0 is 0. So here starting with, this should be starting with 1, because it's actually f of 0 plus this summation, and this is equal to 0. So again, so this kind of recursive formula applies for n greater or equal than 1. It doesn't apply here. And this is how I can find the Taylor expansion of the function. Now, this Taylor expansion of the function, the question is when it is a good approximation to this function. So obviously here, because we did the Taylor expansion for x equal to 0, it means that when you're very close to 0, then this is a good expansion. This is a good approximation. But maybe when you're far from 0, the accuracy of this expansion becomes less and less accurate or useful. Now, the question is, when does this infinite series converge to this function? You can see here that whenever you cut the terms here, right, you have xn. So this xn, so let's suppose you cut it at, I don't know, what, any term. So if you got it at the Lth term, so you have something like, so you have here, if you want to do it, so you have some terms here. Let's suppose you want to take the approximation to the fifth order or whatever. So you have f of x here is equal, if you want to do it to the fifth order, so you're going to have, for n equal to 1, so you're going to have x plus, in this case, for n equal to 2, so you have actually minus x2 divided by 2, and so on, so forth, plus x5, something here, plus something as a function of x6, plus something as a function of s7, and so on and so forth. Now the question, when are these things gonna go to 0? Because these are the errors. And these will go to 0 whenever x is less than 1. And for this reason here, this thing here, the Taylor expansion converges to this guy here if the absolute value of x or the norm of x is less than 1. So whenever you are within that region, then you have a good approximation. Otherwise, outside of the region, the Taylor expansion does not converge to the function f of x. So this is different than the function, the exponential function, where actually you converge in the whole space. Again, I don't want to go into the details how to do these things, but details about the Taylor expansion. So you could go back to your calculus course or consult the Wikipedia article. Now, going back to our problem to find the inverse z transform of this function here, which is log 1 plus az minus 1, and knowing that x of n is right-sided, now I can do the Taylor expansion, like I just did for that example, but here I have the simple difference that az minus 1 instead of x, so I can just use x equal to az minus 1, and I get this formula here, and this is a power series, and I can immediately say that the value of xn of x at the nth time is actually this part here. This is the value of x at time n, and this is what I have here. Let me double check. Okay, at u n minus 1. So yeah, so like I said, so the value of xn, x of n at t equal to n is equal to minus 1 to the power n plus 1 an to the power n. So this will give you x of 1, x of 2, x of 3, and so on and so forth. Now, if you want to write it as a signal, then you know that this x of n, but x of n and x of n is equal, so this is for n greater than 1 or equal than 1, right? Because the summation here starts at 1, or x of n is equal to 0 for n is less or equal than 1, and this is why you have here u of n minus 1 to make sure that everything for all the time with n less or equal than 1, the signal is 0. One more thing here that I wanted to mention is there is another way to get this Taylor expansion here. By noticing that actually you can write, and I want you to do it at home, so you can write 1 divided by 1 plus az minus 1. You can write it as a power series, and we know that here this would be written as 1 divided by 1 minus az minus 1, which is what I know, which is 1 minus az minus 1, right, minus plus or minus az minus 1 square plus minus az minus 1 cube, and so on and so forth. And now if I integrate here and I integrate this side here, then I get, so if I integrate here dz minus 1, I get log 1 plus az minus 1. You have to divide probably by 1 over e here, so let me think about it. So So here you have to do 1 minus a. So either I have to multiply or I have to divide. I haven't checked, but and then you do the integration here too. So you get, for example, the integral of 1 is z minus 1, and so on and so forth. And this is how you get the power series. So I probably have made a mistake doing this or explaining this very fast, but this is to tell you that there is another way of getting, at least in this way, getting the Taylor series expansion. So sometimes you can do it just by applying mechanically the formula that I explained in the previous slide, or you can do it by using these tricks. By you know the Taylor series expansion of something of a function you already know, and then you either derive that function or you take the integral of it, and this will give you the Taylor series of another function that you are interested in. So here I know the Taylor series expansion of this function, which is 1 divided by 1 plus az minus 1. And if I take the integral of it, then I get the log function that I'm interested in. And what is interesting here, it's easy to see why we get the regions of convergence of the Taylor series. So here the regions of convergence, at least if the signal is right-sided, so here the region of convergence of the Taylor series is so this would be az minus 1 less than 1. So this tells you the regions of convergence of the Taylor series expansion. So so here to summarize what we have, so if the function is not rational, then maybe you want to try to express this function as a power series, and then once you express it as a power series, inverting it would become straightforward. Now, how would you invert it? How would you transform it as a power series? There are two ways. Either you apply mechanically the Taylor series formula, meaning the Taylor series expansion of f of x at a is equal to f of a plus f prime of a divided by 1 factorial x minus a, and so on and so forth. But you have to be careful about the region of convergence of the Taylor series, meaning that it could be that the Taylor series, when x is close to a, this is a good approximation, but then when x is far from a, this infinite sum does not converge to f of x. And I gave two examples here where the function e of x, which we say that it is an analytic function, meaning the Taylor series of it always converges to e of x. And the other function that we did is log 1 plus az minus 1.